Okay, I'm back. Sorry about that. I'm kind of OCD about this. I just I had forgotten to push the Notebook 7 annotations that I made onto the Git repo, so I just did that. You'll also notice if you've been there that I made some annotations to this notebook, to Notebook 6 as well. Notebook 7 I didn't do too much with. I just made a few notes on it. But Notebook 7 I put in a little mini review of how convolutions work, just in case people were rusty on them, as I was when I came in here, because I haven't worked with convolutions since the first class, and so they're starting to work. In Notebook 6 we're working with convolutions. I just wanted to put in a little bit of a review. So I guess it'd be good to go through this. I just made some notes here in this cell. So we're looking at this command, getCNN, the function getCNN model, which actually generates our model with the complete model, including 4 convolution layers. And I put some notes here, some little comments that tell us what the size of the arrays that we're dealing with are. So on the input layer, we come in with for one example, we come in with a 28 by 28 image. It's an array that has the image of the digit in it, right? And then the first layer specified by nn.conv2d with inputs 1, 8, 5, padding equals 2, stride equals 2, and then a ReLU afterwards. So after that's done, you end up with 8 channels of 14 by 14. And the second one, after it's done, you end up with 16 channels. That is the second convolution layer. You end up with 16 channels of 7 by 7. The third convolution layer leaves you with 32 channels of 4 by 4. And the fourth convolution layer gives you 32 channels of 2 by 2. And then the average pooling layer, you end up with 32 channels of 1 by 1 because you're averaging all those 2 by 2 things into one number. And then the last layer is just flattened, and all it does is removes, as far as I can tell, it just removes the extra dimension from the end. And then the linear layer maps those 32 numbers into the 10 digits. And so in order to do that, if you imagine you need a column vector, you have to have some way to map a column vector of length 32 into a column vector of length 10. And the way to do that is to multiply it by an array that has dimensions of 10 rows by 32 columns. If you can imagine that, how that works. So each row, you take the dot product of each row with the column of 32, and that gives you one number. But you have 10 rows, and so you end up with 10 numbers. That's how the matrix multiplication works. All right, so just to review how this all works, and so what I want you to be able to do is derive these numbers that I put here. In other words, how many channels are there and what do the outputs look like? Let's go through. So I gave you sort of an assignment to derive those numbers. And I thought I would just, as an example, go through the first one. So I want to go through the first convolution layer and show that, yes, it gives you an output of 8 by 14 by 14. So start with the 28 by 28. We've specified that we want 8 output channels. That's here. This 5 means, so 8 is the number of output channels. This 5 tells you that you want a 5 by 5 convolution kernel. And then we want padding of 2 and stride of 2. And since there's no specification for 0 padding, that means, well, by default, the padding is going to be all zeros. Okay? So let's start by adding the 2 pixels of padding on each side of the 28 by 28 image array. Adding the 2 pixels of padding on each side gives you a 32 by 32 array, correct? And now we want to apply this 5 by 5 convolution kernel to a 32 by 32 array. And I should have drawn pictures for all this, but you'll just have to sort of imagine in your mind. If we line up the 5 by 5 kernel at an initial position at the top left of that 32 by 32 array, that means that column 5 of the kernel lines up with column 5 of the image, and row 5 of the kernel lines up with row 5 of the image. I'm just basically plunking down that convolution kernel at the top left of our 32 by 32 image. And then when we apply the convolution, we're basically going to be sliding the kernel to the right. We're basically going to scan across in steps of 2. That's what the stride of 2 means. So we're going to sort of move 2 pixels and then do our convolution operation, then move another 2 pixels, and then keep going until we run out of room. All right? And you can verify that that gives you a total of 14 positions, including the initial one. And the way I calculate that is the size of the array minus 5, because you have the 5 by 5 kernel, and then the /2 means divide by 2, but discard the remainder. So it's basically just the integer division. And then we add 1 for the first position. And so there are 14, if you can imagine, there are 14 kernel positions going across, including the initial position. So you can imagine that. You can actually even, if you don't like the formula, you can just work it out for yourself by sliding and keep sliding until you bump up against the end of the 32 by 32 array. There are 14 positions. Now, since it's a square array, when you move the kernel downwards, it's the same. So you end up with 14 positions again. And so that's why you have this 14 by 14 array, because it's one position, one value, or one value for each kernel position. And what do we put in those 14 by 14 array elements? Well, each element gets the convolution product. So you take the 5 by 5 array and multiply it by the by the elements that are overlapping in the matrix, right? In the underlying image matrix. So you multiply each kernel element by its corresponding pixel, and then you add up all of these 25 products. And the sum of all those 25 products is a number, and that number is the pixel value at that position. Okay, so the operation, the mechanics of applying the convolution is basically plunk down the convolution filter kernel, do the, form the 25 by 25 products of the kernel value by times its corresponding matrix element, and add up those 25 things, and that's your first value of the matrix. Then you slide it over by 2 to the right and do the same thing. Slide the convolution filter over by 2 pixels to the right, and then do the same thing with those overlapping pixels to get the second value. And you keep going 14 position, all 14 positions, and then you start scanning downwards. So you move, so you can imagine like a raster scan. You just go across and then go down by 2 pixels and then go across to the left and then go down by 2 pixels and across to the right, and until you've scanned the whole array and applied the convolution. And then you end up with this 14 by 14 array. So that's why the output layer has 14 by 14. And then you want 8 convolution, you want 8 channels, which means that you want to do times with different convolution filters, which means that you have to solve for those 5 by 5 convolution filters. You have to solve for 8 of them. Okay, so does that make sense? Are people with me?
Quick question.
Yes,
question, if I may.
Yes.
As you slide this matrix, right? As you slide the kernel, let's say,
yes,
to the right, some of the computations that will be performed are repeated computations, because some of the elements that we're multiplying are the same. There is an overlap with elements with sliding the matrix.
That's correct.
Is there an attempt to reduce the amount of repeated computations and perform each computation only once by storing an intermediate value somewhere and reusing it later as you go along?
Wow, that's a really great question. That hadn't occurred to me, but you're right. There's a lot of repeated computations, and I don't know the answer to your question, but I suspect that I'll wait till somebody has a comment, but let me finish.
No, Joseph. I just wanted to comment that I disagree that there's repeated computations. See, in a kernel, when you're sliding, you are multiplying with a different section of kernel each time. So even though there will be overlap on the same kernel while sliding, I don't think there will be computations which are being repeated. So all the values of kernels won't be same, if I'm
I
assuming.
see. Let me think about this.
Some of the columns in a kernel are the same columns that you're multiplying by the second matrix, whatever the values are there. Is the second matrix that you're multiplying by the same or different? You're multiplying by the weights, right?
Yes, the weights being the weights are the elements of that convolution filter,
right.
The kernel.
So are the weights staying the same for the duration of the for loop?
Yes, the weights for each channel, you're going to do one convolution, and you're going to work with one kernel, the 5x5 kernel, and then you're going to do it again 7 more times because you want 8 channels. So you're going to solve for 8 of these 5x5 kernels. But you're right, there is some, I mean, I agree with Vikas that not all the computations are the same, but there are some overlapping computations.
Right.
And so I wouldn't be surprised if PyTorch tried to optimize by storing some of these intermediate results. But somebody else would have to answer that because I don't really know the answer. That's a really good question, though. Any other questions up to where we are now?
I think on the CPU, it makes sense to kind of store the values as you move along because of the overlap. But on the GPU, you usually will not do that. Oh, someone has mentioned that in the comment too.
Well, GPU is not the only architecture that can perform this computation efficiently. So it's a general purpose question. And the other,
yeah, otherwise, for example, in image processing, you would do that.
Right.
And you can further break this down, usually if it's a 2D filter, you can break it down into 2 1D filters. If that is possible, then if you imagine the number of computations is 25 on this, whereas if you break it down into 2 1x5 kernels, then your computation is just 10 computations. A couple of ways to do it.
Yeah, except there won't be 2 1x5. Oh.
I mean, it depends. If your 5x5 is a linearly separable filter, if it can be broken down into 2 1x5 and 1 5x1 filter, in result, it will give you back a 5x5 filter. But the total number of computations is going to be 2 orders magnitude less, right?
I see. Okay. Well, that's worth looking into. I think I'll take that as a follow-up. I'll try to follow up on that. Anybody else interested should too. That's a really nice question.
And the other one, if I may, if the image was of a somewhat different size, how do you go, what's the guidance on how you go about determining the size of the kernel and the padding? Do you try to make the size of the image on x-axis and a y-axis in such a way so that, you can factor it in a bunch of different, say prime numbers, so that you can try all of these different convolutions? Like in this particular case, we have, 7, 4, 2, and 1. And if we were to come up with a different padding, we would probably have some other different combinations.
It's, I don't really know. I just know that I see that people use 5x5 generally for the first convolution layer, and then they use 3x3s. I'm not really sure why they do that or what it's the way I understand it, and maybe I'm wrong, is that this is more of an art than a science, that people don't really know why they do these things. They just do them because they work.
You mean the hack rather than the art?
Just to answer that, Joseph, I think the 5x5 kernel and padding is kind of related. You want padding to be 5x2, right? Because you don't want, when you're at the corner pixel, you don't want to lose out those 2 pixels out there. So padding is kind of related to how big your kernel size is, which is usually, so if it's 5, then you go 5x2.
So you're saying that the reason that there's a reason why they use a padding of 2 associated with the kernel size of 5 and a padding of 1 associated with the kernel size of 3.
Yeah, so it's basically like whatever your window size is, integer divide by 2.
Yes, yes. I think that's right. I think I've seen that in future codes where they actually calculate the padding size automatically, just using exactly that formula, the filter size, integer division by 2. Yeah, so Prashant is correct.
And a related question, if I may, what are the benefits of using stride equal to 2 as opposed to stride equal to 1?
Reduce computation time for one.
And other than that,
and it gives you a smaller array size too. I mean, at the end, if we had done a stride of 1, we would end up with a bigger than a 14 by 14. It might be I don't know. I should do the calculation, but it'll be twice as big as the 14 by 14, or actually 4 times as big, because it'll be twice as wide and twice as high. So so the stride of 2 is basically giving you some speed up in the computation time, I think.
An intuitive way to kind of understand that is the whole idea of performing these convolutions is you're trying to condense and represent your image in a smaller format so that you can map it at the end of the day.
Right.
That's the way.
I understand. So then by using the analogy, what would be the reason not to use stride 3 or stride 5?
I think that should work too. It's just that you don't want to start with a really big stride in the beginning, then you like lose out all the information. Once you've lost the information, you really can't get that back, right, for your following operations.
Yeah. So what Prashant is saying, you could try. You can start with this stride of 2, and then you can, when you get your results, then you can change the stride length and then see if your results are as good, and if you're willing to make, and if they're not, if maybe they're a little bit poorer, but they're so much faster that you're willing to make the sacrifice. Yeah. So the answer is there's no reason why you can't do a stride of 3 or 4 or 5, and condense the data even further. But as Prashant says, that when you do that, you're losing more information every time you're taking these convolutions. You're actually condensing the data into, you're condensing 5 by 5 pixels into one number, and when you take a stride, that means that when you take a longer stride, that means that you're not. That means that you're losing. Like if you were to take a stride of 1, you would have all the you would have all the data. But if you take a stride of 2, you're losing some of the data, because you're losing the 5 by 5 averages of the intermediate pixels.
No, I understand, Joseph. I was trying to make a connection between the stride size, the size of the original image, as well as the size of the visual features that we're trying to capture. So in this particular case, the images themselves are small, right? So it doesn't make sense to use larger, stride, because you're not going to capture everything. But if your images are 5,000 by 1,000 pixels, if you're doing, radiology type of image analysis, so if you're doing classification of relatively large size of objects, then you probably wouldn't want to use small size stride. So I was trying to make a connection between these two.
I see. I guess so. So you could, if you're doing radiology, maybe you have some feature sizes that are generally prevail in these images. Like maybe there are a lot of 10 by 10 features, or maybe even another layer of 100 by 100 features, and so you might want to design your own convolution filters to explore these different scales. So that's a good point.
Thank you. That's all.
Yeah. All right. So to sum up here, what we've got is we have 8 filters, and they're each 5 by 5. So you can easily make the calculation that 200 weights that we have to determine for this layer. We have to. That's the number of weights that we have to solve for. And the output of the first layer then is a stack of 8 channels of 14 by 14 arrays, which has 1,568 entries. An interesting question then is, how many total parameters do we need for the whole model? So if we start with the first convolution layer, we get 200. Similarly, and you can refer to the comments comments that I made in this function to show you what the other layers look like. So for the second convolution layer, we have a 3 by 3 convolution, and there are 16 channels, so that's 144 parameters. The third channel is a 3x3 convolution with 32 parameters. And again, the fourth is, so that's 288. Sorry, I have to edit this. 288, 144 times 2, 288. Sorry. Okay, that's correct. Final fully correct, and the final layer maps the 32 values returned by the adaptive average pooling layer to the vector of 10 output parameters. And this mapping requires a 32 by 10 matrix, as I mentioned before, which has 320 parameters. So the model has to determine a total of, and I calculated 920, yeah, 920, yeah, plus the 320 for the final fully connected layer. That's 1,240 parameters. And this is for each. So for each image, we have, for each of the input images in our input sample, we have to determine 1,240 parameters. And the interesting point is that the data itself only has 784 data points. You know, the 28 by 28 array has only 784 data points. So the model has more parameters than data points. And this is really strange. People didn't usually like to deal with systems like this, where there were more where there were more parameters to be solved for than the inputs that you have. And previous to neural networks, people avoided these kind of systems like the plague because they believed that they wouldn't get good answers and so on. But it turns out that stochastic gradient descent gets you a good answer, even in the case when you have more parameters than data points. So it's just, that's the basis of this revolution in neural networks that has been happening since 2012.
Just a point there, those 1240 parameters are going to be consistent across all your training images, right? So it's basically you have 28 into 28 into number of training images that you're working with.
This is a very good point. You're not going to have to solve for these. Let's see, are you? You know, I'm not sure about that. I'm not sure that you have. If you
think of it the way you run your batch, when you pass in a batch, you're not passing in one image, right? You're passing in like a batch of 32 images.
Oh, okay. Your point is correct then. Yeah. So it's exactly the opposite of what I said. You only have to determine 1,240 parameters, but you have 50,000 images, each of which has 784 parameters. So you have way more parameters than you need to, way more data points than you need to determine the small number of parameters. And I guess that's one reason why convolutions are so fast, because faster than fully connected, than a fully connected layer, because that would have way more parameters to determine if you just had a whole bunch of fully connected layers instead of convolutions. Okay, so thanks for that correction, Prashant. That's right. So anyway, I'll have to edit this thing to take account of what Prashant said. All right, so that's the end of this little mini review. I hope that was useful to people. And let's see where we stopped in this. We were doing hooks. Let's see, where does hook start? There we go. So okay, so we were talking about hooks, and hooks give us a way. They're a built-in from PyTorch, and they're kind of like built-in callbacks that work in these nn.module layers. And they're specially designed by PyTorch to work in these, they're basically specially designed a callback structure that you can use to do things inside of the layers. And the example that we use here is we calculate mean and standard deviation. We calculate our statistics inside of these layers for each layer. And so let's see, let me go back up here, create the model. So far we haven't used any hooks yet. We've got this sequential model. We build the model. And I put this little statement in here so that I can see when the initialization gets done. And when I create the model, I see that it gets done when I, as soon as I, excuse me, as soon as I create the model, this thing, as soon as I instantiate the model, this thing gets, the initialization gets done. And I also put a statement in here in the call part to understand how, when it gets done. But I didn't get much satisfaction because it never executed. I never saw it. So let me put that. Well, actually, no, I did see it. Let me put this call, a little marker to tell me when the call statement got executed. And I should put it up here. And I can't say that it just executed. What I can say is that it is executing, that it will execute. Because after it executes, after it finishes executing, it returns after the end of this loop. Oh, I guess I could move it down here. I'm trying to understand what the difference between these, or when these when the init statement gets done and when the call statement gets done. So I'm going to compile that. And the note that I found when, I found this in the Python documentation, it says that the init method happens when the class is called to initialize the instance. So that would be here when we initialize the sequential model class. And the call happens when the instance is called. And so that means when the instance being this thing called model, this object called model, and when the model is called, that's here. So we would expect to see that init executes when model is instantiated. And then the next cell we would expect that that's going to initiate, that's going to execute the call. So let's see if that is what we get. So create the model. Oops, what happened? Did I do something wrong here? I think I have to execute. I think I have to start at the top and execute this thing. So hold on for a sec. It's very quick, so just get down there to where we were. Keep going. I got too many. And then this, and then this. Sorry about this. I have to execute the notebook to get down to where we were. This is just a demonstration of CUDA being faster when you can use the GPU. Okay, so you see that we had done one epoch. I might as well make comments as we go. You can see that with the CPU, we did one epoch in 11 seconds. With the GPU, we did 3 epochs in 3.83 seconds. So, 1.3 seconds per epoch versus 11 seconds per epoch. That's about a factor of 8 or so speed up. So, okay, now let's keep going.
Quick question. So is that the maximum amount of speed up that's possible, like factor of 8 with a GPU versus a CPU?
That's a good question. I don't know the answer to that. Maybe there's tricks to make it faster.
If that's all one gets, then it's really not worth it. It's cheaper to buy like a commodity CPUs than a very expensive GPU and
the cheaper it gets, the faster you.
Huh?
the deeper you kind of get, the faster it becomes. You'll get like orders of.
Yeah, so this is so that's a good point. The factor of 8 is specific to our network that we built here with the 4 convolution layers. And what Prashant is saying, that it's possible to build layers with many, networks with many more layers than that, even up to 1,000 layers. And that's where the speed advantage comes in, I guess. So don't think this factor of 8 is the answer. It's just the answer for this particular network. And I think a factor of 8 is pretty significant, because, if you can imagine trying to train a model and waiting an hour for a result versus waiting 10 hours for a result, that's a significant difference. Or even a minute versus 10 minutes. 10 minutes you have to go away and get a cup of coffee. 1 minute you can just sit here and twiddle your thumbs, and and it's much more comfortable to work that way. Anyway, continue. I just need to execute to get down to where we were. This is a huge notebook, by the way. This is one of the biggest notebooks I've ever been through here with this class. The next notebook is smaller. Okay, so here we are at hooks. So let's do, we're still executing this thing. Now we're where we want to be. Okay, so I want to do that. See, and as we expect, the init method happens when the class is called to initialize the instance, and that's what's happening here. The class is being called to initialize an instance, and init just executed. Now we're going to create the learner and runner objects, and this is when the model gets called, and that's when we should see the call method happening. So, and this is strange. I don't understand why I didn't see an output. So I did this experiment before, and I didn't see an output, so that's why I erased it. Anyway, then you can do things like look at the model. I like to use dir dir on the model. It shows you all of the it shows you everything you can get at. It shows you everything that's available to you, both the hidden methods and properties, as well as the ones that you're meant to be able to get at. So by doing a dir on an object, you can see all of its properties and methods that you can get at. It's really helpful. So anyway, that's that. Now we're going to initialize this ACT. What does ACT stand for? Anyway, I don't know why he calls it ACT. We're going to
activation
initialize.
Means.
Pardon?
Activation.
Activation means. Okay. I hate these cryptic words. I wish they would just write it out. It doesn't take that much more time. All right. So activation means we initialize this one mean for each layer. There are 7 layers, so we expect 7 means. And the model knows that. The model knows that it has 7 layers, because if you do this, if you do len of model, oops, I thought it had. One time I saw this. I thought length tells you how many layers it has. All right. Anyway, let's move on. All right. So there are 7 layers, and so now we're going to train this model. Now it's executing all of my. Yeah. At each epoch, it's running through all of these. And I imagine that you would see all the batches. The number of times it executes is the number of batches, I think, or the number of, I'm not sure what it is. Anyway, I'm going to comment that out, so I don't want to see that. Do that again. Go here, do this again. Okay, now we won't see all. We just see the 2 epochs. And at the end of 2 epochs, we got to 81% accuracy. I noticed that these plots down here are of length 216, so I wanted to find out. Let me just put this down here. So I labeled, I think that what we're seeing on the horizontal axis is sample number, but I'm not really sure. So the number of means that you get is 216. And if you run one epoch instead of two epochs, then you'll find that it's 108. So I'm really not sure why this is 108 and 216, given that the batch sizes are bigger than that. Sorry, each batch, I think let's see. I'm going to interrogate here, find out what the batch size is. I think the batch size is 512, right? So it's 512, and we have 50,000 training examples. Does that work? Yeah, I guess it does. Each batch has about 108 in it. What's 512 times 512 times 108? Oh, okay. And the last batch has fewer. Okay, that makes sense. Okay, so we're looking at in a batch, and I believe it's taking the mean over all the batches.
I think I missed that. What did that tell you about the number 260?
Okay, when I did this with two, remember we did this with two epochs. And then we had 216 numbers in our 216 values for the mean. But look at this. Suppose that I ran it for one epoch instead. Now let's plot this again. Now remember, this is 216 here. I'm going to run this again, and now it's 300 and something because it's adding all of the ones from the 216 I had before for the first two epochs, and now it's adding the third epoch, which gives me another 108. So, but let me start all over again to show you that one epoch gives you 108. So I'm going to start again. I'm going to just run one epoch. And now make the plot. And you see it's just added another epoch. Somehow I didn't go far enough up. I have to initialize everything. I have to initialize everything from the beginning. So, but not from the very beginning. I thought it was enough to create the model, but maybe I have to go one step back. Yeah, this should be good enough. If I start here and create the model, create the learner and runner objects. I don't need to see the means. Now before I run anything, this time the means should be all 0. Yeah, or not 0, but as they were initialized. And then see what happens is this model.act means accumulates all the means as you train the model. So this tells me that it's all initialized, nothing's happened yet. So now I'm going to train for one epoch. And now I'm going to make the plot. And you see there's 108. There's 108 means that are. And what I claim is happening is that it's taking all the batches and averaging the means together. And this is the calculation that I did. There are to sort of help me to believe that there are 512 batches, and I claim that what we're seeing is the individual samples in the batch. That's what this 108 is. And to verify that, let's multiply. 512 times 108 gives me 55,296, and I have something like 50,000 training examples. So I believe that's what we're seeing is the elements in the batch, the sample number in the batch. And I think since this is cumulative over the whole training, we're actually averaging all the means from the first sample in the batch, second sample in the batch. In other words, all 512 batches go into each of these numbers. Does that make sense?
Okay.
Okay, so that's why we're seeing 100. Now, if I ran 2 epochs, if I started from scratch and ran 2 epochs, then this would be 216, because I get, the 512 batches of 108, but then I run it all again. So, because I'm running another epoch. 512 times 108 is 1 epoch, and then another epoch is another 512 times 108. So then we would see 216 numbers here from 2 epochs. And if we did 3 epochs, we would see 324 and so on. Does that make sense?
Yes, thank you.
Okay, and let me just demonstrate that once. Let's suppose we wanted to run, I'm going to initialize the model. And let's suppose we want to run 3 epochs instead of 1. Run 3 epochs. It's very quick, so this kind of experiment is cheap. All right, and now we can look at the plot. And remember what we expect is we're going to see 324 samples here. And there we have it. And if we ran 2 epochs, there'd be 216 and so on, right? All right, so let me just, so that I won't screw up the notebook, I'm going to put it back to 2, which is the original. That's what it had originally. Okay, now let's just continue. All right, so what is he doing now? Sample number. Oh, now okay, so that plot was for the means. Now we're going to plot the standard deviations. And again, we're going to see 316 because we trained 3 epochs. And there they are, the standard deviations. And we can just sort of note what's happening to the standard deviations. They're starting out at close to 0, and they're sort of trending upward. Standard deviation of 5, it's not terrible, right? I mean, you want the standard deviation to be close to 1, and 5 is much bigger than 1, but it's not 5 times 10 to the 6 or anything like that. So at least it's staying under control. And the means, we want the means to be close to 0, and they're drifting away, but they're not getting too large. They're not 8 times 10 to the 7th or anything like that. They're 0.8. So that seems like things are going well. Okay, now what this is doing is it's just zooming in and looking at the start of what's going on at the beginning of training. And so, and these, remember, these are the different layers. So 0, 1, 2, 3, 4, 5, the 5 layers. Remember, there's actually 6 layers here. The reason why they skipped the last one, I'm not sure why they skipped the last one. There's 6 layers. There's actually 7 layers. The 7th layer is the fully connected layer, and they skipped that one in the plot.
The last one's kind of the linear layer, not the convolutional layers.
That's right. It's a fully connected linear layer. Let's just see what happens if we ask for the set. I think it's going to crash, but let's see. Oh, it gave us 7 layers. So yeah, you can see all the layers. And the 7th layer doesn't behave too much differently than the green one. So yeah. All right. So, and since I did that, I might as well do that here as well to look at the standard deviations. On that, let's see that. Okay. Okay. So now we get into the hooks. And what happens is you don't, the hooks get added in after the fact. So you get to create your model, and you don't have to worry about the hooks. The hooks get added in after the fact. You don't have to rewrite the model. So again, we're going to create the model, the runner and the learner objects, initialize empty lists of the correct size to contain the mean and standard deviation for each layer. So that's what we're doing here, initializing. I don't understand why I can't, I can't look at the length of the model. Why can't I why won't it give me 7 when I do this? Yeah, it does. So why didn't it do that last time? I don't understand. Maybe the model hadn't yet been initialized. I think that's what it is. So when you take the length of the model, it just tells you the number of layers. And so this called a list comprehension. This is why it works, because you iterate through. You don't care what these things are. It's just you're going through the layers.
The previous model, Joseph, from what I observe, is that you were initializing it with the sequential model. Here you're using getCNN model. So I think sequential model doesn't have length defined, whereas getCNN model has length defined.
Ah, good point. Okay, good point. Okay. So what I would do is, instead of using this cryptic notation here, this is what I do when I go through these notebooks. I'm really OCD about this. I rewrite them the way I like them to be. So, instead of using dash, I'll put layer, because that's what you're really doing. You're iterating through the layers in the model, and for each layer, you're initializing a mean. You're initializing the mean to be an empty element. So, okay, now the hook is attached to the layer. And the hook is a function. Since a callback is a function, a hook is also a function, at least initially. So this is, well, no, a hook is more than a function, but a hook needs a function. In other words, the hook is going to execute some function for you inside the layer. And so this is the layer this is the function that you want it to initialize, to execute, sorry. It's called append stats. And it takes as its input the layer number, the module, the input, and the output. And it just goes through and appends to the list of means the mean of the data. And then it appends to the list of activation standard deviations, the standard deviation of the data. So that's what it's doing. It's just building the list for each layer, the list of means and standard deviations for each layer. And next, you have to register. That's the way these hooks work. You have to quote unquote register them. And there's a special function for that that's built into Python, built into PyTorch, called register forward hook. And there's another one for register backward hook and so on, but we won't see that yet. So you're going through, again, you're going through the layers of the model. I is the layer number and M is the layer. And you're going to register the forward hook. If I would rewrite this, I would write it this way: I layer, the index of the layer, and layer is actually the layer itself. That's how I would rewrite it to make myself happy. And then we can look at this register forward hook function to see what it does.
Shouldn't that be I layer, Joseph?
You're right. Thank you. Thank you very much. That's a good catch. All right. So what does this forward hook, register forward hook function do? It creates this thing called a handle, which is a property of hooks, I guess. I don't want to get into all the weeds here, but you can actually see, if you spend more time, you can actually see what's going on under the hood here. We don't have time to do that, so let's see. This is funny. I meant to get through the rest of this, and I haven't, and I meant to get through 7 as well. And we're not going to get through notebook 7, but maybe we'll get through this one. All right, so now we train again. Let's see. But we've registered all these hooks that are now going to be happening inside of our model. So now the act means has been populated after we ran the training set. I should have shown what happens before and after we run the training set. Before we run the training set, the act means is just going to be these this list of empty elements. And then after we run the training, it's going to be populated. And so now we're going to actually plot what's going on. What are these means? So. And remember, we've done 3 epochs, so we expect to see 324 of them, I think. Oh, something's wrong. To go back, I'm gonna have to back up. I think I messed up. Okay, go back. Go back. I think I hadn't corrected this. I think that was the problem. So let's do the train. Oh, now we can, before we do the training, we should be able to see these means, act means, and they should be empty, I think. Yeah. Now we run the training, and we got up to 78% after this. And now let's have a look at act means. Oh, interesting. Why have we not got anything in there? Something went wrong. Register forward hook. Maybe it. Maybe I better go back to what they did.
You're doing m.register instead of doing layer.register forward hook.
Thank you so much. Yeah, because it used to be m. I layer. Yeah, so this is the perils of refactoring. You have to make sure you do everything right. So I just think that this is much nicer, for me at least, when I look at this, I understand what's going on. When I look at the original, it's not clear to me. So let's do that. Let's see again that we have an empty set there. Now we run the model training. And, oh, now we've got a better result. Now let's look at the means again. And see, they're populated. They're populated with all the elements that I should just go, instead of looking at them all, I can just go length of act means of 0. Just look at the length of the first element. Oops, means of 0. Oh, length of act means of 0. All right. Yeah, 108. All right, so now we're going to plot them. And okay, let's see, there we are. And things look, you know, in the first time I ran this, the means were unstable and they were spiking upward. I made myself a note about that, but this time they're not. So I'm not sure why. Anyway, so now he refactors things as Jeremy does, and Jeremy and Sylvan do. They like to, once they get something working, they like to make it nicer or more powerful. So now they've defined this class, and it has an init method, which basically just consists of register forward hook, which you have to do when you define a hook. And then he has to define this remove method and a delete method. And I'm not exactly sure why, but I think that it has to do with the fact that once you populate the means and so on, then if you run it again, then it's just going to append on top of that. So if you want to really run again fresh, you have to somehow remove what you did before. So that's why it has to have this remove and delete methods. And then we have, again, this append stats method, which is the same as before. All right, so now we should, oh, and I just wanted to show you the callback functions list now. It has the recorder, that's one thing. The batch transform callback. Oh, there's 2 of those. Why? Let me just look at this. I want to see how many there are. I wonder why. Remember, callback functions, CBFS, which should be named callback functions, is a list of callbacks, and it has 5. It's a list of 5 callback functions, and it has 5 of them, and we can see them here. It has func tools. It has recorder. It has func tools, accuracy. This is one class. So it goes all the way down to Oh well. Function view. Sorry, I'm just looking at the, getting lost in the details. Let's continue. So now we're going to run this thing again with the newly constructed hooks thing. Create a list with a hooks class corresponding to each layer. So hooks is basically running through this hooks class. This is what's called a list comprehension. So it's running through and executing the hook callback. And why can we do that? Because the hook callback has all of these methods have all of these classes have call methods. So, it's not inheriting. I think it has implicitly, it has a call method. So you can actually call it as a function. And we're going to do this. We're going to iterate through the first 4 layers in the model. So now we run the, whoops, I have to do this again. Huh? What happened? List indices must be integers or slices, not hook. What did we do wrong? Model 4L x equals hook L. Maybe I forgot to do that. Yeah, I hadn't gone back far. I had to execute this cell here before I started. So, all right, so now it trains 1 epoch. And now we're going to do the same thing, make the plots. And there's this weird spiky behavior, which I don't understand, but it's not terrible. It's only, the mean is only spiking to 1.6 and you need it to be 0. So, but then it's getting back under control. So it spikes up and then it gets back under control, and that's what keeps happening. But it is drifting away. So, okay, I wanted to see how many batches. Okay, this tells me how many batches I have. And why? Okay, so now I'm confused as to why I had 108. Okay, 98 batches. Why are there 98 batches?
Quick question, Joseph. After how many data points on this graph we go through the entire input data set?
How many data points would go through the entire?
Right.
I believe this does represent the entire input data set.
So the end of the input data set is the rightmost point on this chart.
Yeah.
We don't go through it more than once in this particular case, right?
That's right. That's right, because we only ran 1 epoch. But now I'm a little confused because my calculation before.
May I ask you a follow-up question?
Yeah,
so at which point do we go through all the digits in the input set? Is it after about 40 data points or sometime prior to that? Is that the reason why you have a spike?
Oh, this is a good question. Yeah, because, well, if the digits are randomly distributed, then you would expect it might take you like 40 or so. That's a good point, to get through all 10 digits. So maybe that's what's happening there, is that at that point, it's seen all the digits, and so it gets a lot better.
Or maybe there is a cluster of some other digit that perturbs the behavior, so.
Yes. Yes, that's a really good point. Thank you. All right, now I'm going to try to unconfuse myself here, but I'm not sure I'm going to be able to do it. So if I ask for how many batches are there, I can ask for it tells me there's 98, and if I multiply 98 times 512, I get 50,176, and that is the number that's close to the number of samples I have. I know that. So let me ask for how many samples I have. Length of data dot train ds dot x. That should give me the number of samples I have. That's the number of samples. That reminds us. So So now I'm a little confused because I don't, and the confusion is I don't understand this number of 108. Why are there 108 numbers being, and why are there 108 means being plotted here? I was thinking that each one of these represents sample number X. So for example, 20. I thought that this number represents the mean of all the sample number 20s in over all the batches. So,
Joseph, can you again do length of activation act underscore means of 0?
Yes. And it's 108. So there are 108 means being calculated, and I need to understand what that number 108, where that number 108 comes from. There are 98 batches. Each batch has 512 elements in it. So my labels for this horizontal, my labels, which I've always put sample number, I'm not so sure about what I'm labeling here. So I'm not sure about that.
I'm not very sure, but I think that 98 and 108 kind of makes sense because that last 10 is for that linear layer which you have assorted like 10 numbers. I'm also not very sure about this graph. I've been trying to debug it myself.
Very good. Very good. So 98.
There are a couple of things, yeah, there. I still don't understand how 98 comes.
Yeah, well, 98 we understand. We understand 98. I understand 98 very well. It's 98 is the number of samples in each batch.
Oh, okay. And
yeah.
512 is your number of batches.
Sorry. 512 samples in each batch, 98 batches. 98 is the number of batches that we have.
Okay.
Yeah, but I don't understand 108. That's what I don't understand. We can just while we're here, we might as well ask for some other numbers. We could ask for length of data.valid ds, which dot x, which we think should be 10,000. I think there's 10,000 examples in the validation. Yeah, and then we can ask for what is the how many batches are there? This is training batches, but we can ask for how many validation batches are there. We'll see how many validation batches are there. Okay, I know that some people have to leave, so thank you. Christine, I know you have to go. You might be already gone. Anyway, thank you for those who have to leave. I'm just going to continue for a bit if you guys can stay, if anybody can stay. How many? So I can ask for validation. Probably Prashant has to go too, right?
No. How many images are we working with? Is this 50,000, right?
Yeah, 50,000 in the training set, and there's 10 batches. There's 10 batches in the validation, and the reason is that we doubled the batch size, I believe.
But why? I mean, so 512 into 98 is giving me 50,176, right?
Yeah. So that means that the last batch has fewer. The last batch has fewer number in it. So actually, the last two batches, 98. Oh, 5176, and the number. So why did we have to take 98 batches when we could have taken 97 batches? 97 times 512. 97 times 512. Oh, is not enough. Okay. 97 times 512 doesn't get us to 50,000, so we need that extra batch. The last batch then has fewer than 512 in it. It has what? 336 elements in it. The last batch has 336. To make up the 50,000.
Oh, okay.
Right. And then the validation, we see that there are 10,000. There are 10 batches, so that means that each batch is going to be the batch size for validation. is going to be twice as
Nothing
big.
to do with validation, right? Because everywhere, whenever we are looking for the stats, we do if model.training. Or
yeah, that's what's not clear to me. Is are we looking at the training?
Yes.
Is it automatically?
Everywhere we are looking at training, because if you look at all your active act means or act stands, you're doing them all within the conditional self.training.
Yeah. So I was just noodling around here trying to see what is going on with the validation data set. There are 10 batches and there's 10,000 data points. So each batch is 1,000. And I believe they did that because the validation, remember, with validation, you don't have to run back propagation. So you have a lot more memory freed up. So you can double the batch size. That's what they did. All right. So we have this. So now he's continuing to build on this. I don't know how many, let's see, how many people do we still have and how many people can stay? I can stay. So if people want to stay, I'll be glad to continue here. To at least finish the sixth notebook. All right, so let's see. Now he's building this class called list container. It has an initialization method. It listifies the input items. It has a get method, get item method. What's going on here? Instance, int slice, returns, instance ID. I'm not sure what's going on here. If is instance. It's just, I think these are just general methods to handle lists, whether the list is made of, whether you can, well,
different
it allows you
to
get slices. It allows you to handle lists that are masks, that are Boolean numbers, and so on. I'm not going to get into the details. Yeah, somebody had a comment?
No, that's all. It's just different options for you to index into that.
Yeah. Different methods to handle the list, to get into the list. Okay, then it has a length method. It has an iteration method, so you can iterate over the list. It has a set method. It has a delete method. It has a represent. That's just a representative string that it returns, I believe. Yeah, it's just building a string that gives you the name. All right, so let's just execute that and see how it uses it. So list container, and you just pass in an item, which is basically an iterable list of, and it returns. So this is the represent function. It builds this. When you call it, it just gives you this brief description of what you have. That's what's going on here. And then let's see. The interesting thing is when you call list container, you immediately get a result. Does it have a? I think it has an implicit call method that's doing that. Just to verify that, let's do a dir on list container. And I'm thinking it has an implicit call method, but it doesn't, so. Well, I'm wrong. Okay, well, let's just continue. So here's list container with an iterable list of 10 items. Here's a list container with an iterable list of 100 items. And you can see that it behaves like you'd expect. So now we just build this list container.
Sorry, Joseph, I think that's not because of the call, that's because of set item that is there. I'm not sure.
Set item.
I'm guessing it's because of
self.items equals.
I think it's because of iter.
Iter should help you iterate through, right?
Immediately iterate through the list.
Yes.
But isn't this populating the list and not, asking for values, right?
It's actually populating the list, yeah. So that's what's, you've actually called this thing and it's behaving as a function. It's actually generating an instance of this class. So, okay, that's what happened. So now we generate, we do this again. We generate an instance of the class, and now it's demonstrating these methods that we have of indexing into it. So, you build this thing called T. Now you can take a slice. You can index it by a mask. And that's what the second thing is. And the mask can be composed of slices, so it's very powerful. You can get, you can index into this list. They built in those methods. That's what, as Prashant said, that's what these get item methods are, allowing you various ways of indexing into the list. So this is a nice object. So now we use this to write a hooks class. So hooks now inherits from this class that we just defined, and we initialize it. We do the super init, so it's initializing in the base class, and we pass hook mf for m and m's. M's. I'm not sure what this is. Again, they're using this very compact notation, which is really, to my mind, counterproductive. They should be not so lazy. Write these things out. Make these names descriptive and write them out. Don't have to be so lazy. You don't have to write a one-letter name. So anyway, that's just me raving. So all right. So hooks. We have a delete class. We have a delete item. We have a remove item. That was a prerequisite for this. Okay, and now we're going to use. Okay, the export means that he's going to. This is something finalized. He's going to use it for later. So now we'll run this thing all over again and create this list of callbacks. So the input is model and function. That's what we see here, model and function. And see, I would rewrite this, but I got in trouble. I got burned last time. When I try to rewrite things to be nicer, then when they get exported, when I export my things, it clashes or collides with the things that they've already built, which take these little tiny little variable names. So that's why I stopped rewriting things my way. Things that are being exported, I'm just going to leave it the way they did it because they're going to use it. They're going to expect M and F and M's and F. So I can't really rewrite this to be nice. All right, so this is what it looks like. It has 7 things in it now. Hooks.remove. That's that method that we have for removing it. So hooks now has something in it. So we're going to demonstrate this hooks.remove method. Now we can write. We can see that. We can see what hooks looks like now. Oh, it still has 7 items in it. I'm not sure what this remove function did. All right, next. Okay, so now we're going to generate a batch. That's what this structure does here. Next, of iter of data.trainDL. Remember, data.trainDL is the data loader for the training set. And to get a batch, we iterate on it and we take the next element. So, and then we expect X to be one batch of images, and Y to be one batch of labels. So let's look at that. And there we have one batch of images, and that's x.shape. And then we resize this thing, because remember, we're going to make it into, remember the way the data comes in, each image is in the form of a vector. It's flattened. And so we have this, we built this function earlier called mnist_resize, that takes the input object and resizes its 28 by 28 array and puts it on the GPU. So that's what we're doing here. And when we ask for, after X has been processed this way, we ask for its shape, and it's now been resized, as we see. And I'm not sure, oh, and they put this extra dimension in front because eventually we're going to build channels. We're going to have, this tells me that there's only one channel of input images. Suppose you had RGB images, then this would be 3. Then you'd have to, unpack the images into 3, the RGB images, and then this number instead of 1 would be 3. So it's just a placeholder here telling us that we only have we only have black and white images, not color images. Okay, so now we take the mean and standard deviation of this particular batch, and okay, that's fine. And then model of 0, that's the first layer acting on our batch. and we take the mean and standard deviation of that. So what we're doing is we're running the first layer, which is, remind ourselves, what's the first layer? I believe it's just, oh, it's the first convolution. Okay, fine. So the first layer is the first convolution. Where are we? Here we are. And now we're looking for layers that are sequential, that are in the sequential class. And for each layer that's in the sequential class, we're going to do Kaiming normal initialization with zeros. So that's what's going on here. And for the biases, we're going to initialize them to zeros. So that's what we're doing here. And now when we take the mean and standard deviation, we should, well, I was thinking we would get something, well, the mean gets close to 1/2, and the standard deviation gets closer to 1. So that's good. That's what Kaiming normal initialization is supposed to do. There's no, Kaiming normal, remember, it wasn't, we would like the mean to be 0, and Kaiming normalization doesn't give us a mean of 0, but it does get the standard deviation closer to 1, and that's good. Okay, now we have, having given an enter and exit method to our hooks class, we can use it as a context manager. What does that mean? Let's go back and verify that we do have this enter and exit class. There it is. Enter means return self, and exit means remove self. That's fine. Okay, what is a context manager? A context manager means that you can call it like this. You can use with as. You can use the with as structure to call it. So with hooks model as hooks, then we can run our training. Again, we're just doing the same thing. We're running it for 2 epochs. Where do we specify? There it is. We specify that we run it for 2 epochs. And there's the 216, which we expect. Still trying to explain why that number is 216 and not 2 times 98, but that's neither here nor there. So again, we see this behavior. The first row is, the first column is mean, and the second column is standard deviation, I believe. And the first row of plots is just a zoom of the first the first 9 samples or whatever. And then the second row of plots is the whole thing. Okay, so we see that the means are sort of stabilizing towards 1/2 or 0. It's not too bad. And the standard deviations are also not too bad. We'd like them to be 1, which is going on here. And these two are a little bit more wild. But again, 4 is not that much different than 1 when you think that they could be 1,000,000. You know, the numbers could be 1,000,000 or 1,000 or whatever. So the Kaiming normalization is keeping things within reasonable bounds, I guess. Okay, now he wants to, let's store more than the means and standard deviations and plot histograms. So what do you mean by more than the means and standard deviations? Means and standard deviations and so he wants to store the histograms as well. Hook.stats. Where do we have a stats method? I forgot where. I mean, I don't know where we have hook. Is hook a built-in function, or did we define it? I'm not sure. So it seems to me at this point that it must be a built-in, a Python, PyTorch built-in. Means.append CPU. Okay, so he's using the CPU to calculate the means and the standard deviations and the histograms. I'm not sure why. Oh, and the reason he says that, he makes a note of that somewhere in the video, that the histogram function is not implemented on the GPU. So you can't get it from the GPU anyway. So basically we're refactoring the append stats function to include histograms. We can write that here.
Hook stock stats is just initialized about that to all zeros, Joseph.
Pardon?
Right there, hook stock
Ah,
stats.
there we go. Hook.stats. Okay, thank you. Yeah, I thought that. So hook is not a built-in. It's something that we initialize.
The capital H, that is also a class we define.
Thank you. Okay. So he's refactoring. Remember, he had this append stats function already, but now he's refactoring to include histograms. Histograms. And let's see what happens. Now, model data, CNN model, get CNN model, that's a function we had. Build the model, put it on CUDA, put it on the GPU, get the learner and runner objects, and then for L in model, okay, so we're running through the layers of the model, and in each case, if the layer is an example of a sequential layer, in other words, if it's one of our convolution networks, then we're going to do the timing initialization. And then we're going to use this context manager now. Remember the structure of the context manager is a with as statement. We use the context manager to train. Then get the histogram. I was looking at this function get hist, and I'm not sure that it's a histogram. I need to spend more time on this, but I didn't do that. This thing here, this is a really weird function. Log1p means take the natural log of the function of the object and add 1 to it. Make the natural log of a value and then add 1 to it. That's what this log1p function does.
Log 0 is kind of undefined, so that's why you want to stay safe and use log 1.
That's right. It just makes the thing behave, because if you, that's right. Yeah. So that's that. So we're actually looking at the histogram of log values, I guess, rather than the histogram of values. So for standard deviations, the log of that would be the log1p function of a standard deviation that's near 1 would be the natural log of 2. And the log1p of a mean that's near 0 would be the natural log of 1, which is 0. So the zeros should be the means should be concentrated around 0, and the standard deviations should be concentrated around log 2, natural log of 2. But anyway, that's what is going on here.
For the means, you still have that 0.5 because of the ReLU?
Yeah, that's right. That's right. So 0.5, so then the natural log of 1 plus 0.5 is where we'd expect the means to concentrate.
I still don't understand the histograms fully, though.
Yeah, I don't believe it's a real histogram. I'll have more to say about that next week.
Okay.
Anyway, get min. So he defines this get min function, and all it does, I'm not even sure I understand this function, but let's just go on. Plots these things. What are we plotting? We're plotting get min. Well, whatever it is, we see that whatever these numbers are being plotted, they're concentrating around near 1. So that's a good thing. That's a good thing.
There, actually, Joseph, this is what Jeremy says, is that with that get min, you're trying to look for what percentage of your values in your activations are close to 0. That's why he's using.
Okay.
So it's a bad thing that 80% of your values are near 0.
So it's a bad thing. Yes. Okay. Thank you, Prashant. That's very.
Yeah, I still don't understand this fully. So probably, we should probably stick our heads together again next time and try to understand exactly.
Yeah, but let me make a note here. What you said is that we're getting get the.
If those are the values at the output of, let's say, each layers, then you do want them to.
Those are not the values. That's the percentage of your activations that are close to 0.
Activations being what?
That is what your filter values are basically you're trying to set. So if you look at the getMin function, at the last you're returning h1 colon 2. So that is basically column 1 and column 0. So column 0 will be all basically zeros, column 1 will be close to zeros, and he's doing a sum of that divided by the total sum.
So where are these activations if I'm going to look at the neural network? Where?
That's basically sitting in h1.
at the output of the first layer?
This is for all the layers. I don't think this is for a specific layer.
Right. So it's for all the layers, right? So,
Yep.
so that would basically means that you train your neural network and you wanted to classify things properly. So you would expect that very few activations would be firing and most of them would not be.
No, other way around, right? You want more of pretty much all your activations to be firing and less of them to be zero.
Yeah, because the ones that are zero, you're basically wasting your CPU because they're calculating nothing.
Well, that's the point, right? Because you want the ones that are tuned, that are looking for a certain pattern to fire, and the ones that don't find the pattern that's supposed to find, don't not fire.
If you take it to the other extreme, let's say all your activations were zero, then you pretty much, your neural network is not going to work, right? Well, I agree you're supposed to find the patterns, but at the same time, zero is not going to, I mean, zero may be an inherent value to find patterns, but like having 80% of them to be zero is really not going to be helping you. Yeah,
so as Prashant says, we want the fraction of activations near zero to be as low as possible, and we're not getting that here. Let's just note here, this 2 means that he's looking at the histograms. Remember, h.stats has 3 elements now because he has means, standard deviations, and histograms. And so the second, the index 2 means the histograms.
Yep.
Right? So that's what we're doing here. Okay, let's move on here. He defines this generalized ReLU, which works better than the normal ReLU. I believe, I wish I had a picture of it. In the lecture, he has a picture of it. I think it has, well, we can look at it, what it does. It has an option for a leaky ReLU, and it has an option to be cut off, to have a maximum value cutoff, which isn't being used here. And I don't know what this sub means. There's another option. So
that's that -5 that you want to subtract.
Subtract. Okay, right. So very good. Okay, so, gosh. All right, so leak is, okay. This is Jeremy's trick to get the mean down to 0. I think this is what I'm surmising, that max V means don't allow the value to be above a certain cutoff. If it is, set it to be the cutoff.
Yeah.
All right, so this is just basically a regular ReLU with these modifications on it. And he's going to choose the leaky ReLU from the, see, remember F is this PyTorch built in, and it has all these useful functions that often come, it has all these functions that are useful when you're building networks. And one of them is leaky ReLU. So he is calling this leaky ReLU function. And the leak can be specified. If it's none, then you don't need the leaky ReLU. Otherwise, let's see, if it's not none, if self.leak is not none, else f. Okay, this is that weird structure. So the output is going to be this if you specify a leak. Otherwise, it's just going to be a normal ReLU. That's what this construct is. And then he says if the subtraction switch is not none, then you do the subtraction. Sorry, it's not a switch, it's actually a value. You can actually, I believe it's, you actually tell it, you actually give it the value of 0.5, I think. And then if the max value is specified, you apply this clamp max function with the max value. So this is the generalized ReLU. Nothing fancy about it. It's just a leaky ReLU with an option for a subtraction and a clamping to maximum value. All right, so then he has this init method to timing normalization. if it's a convolution layer, then you do the Keiming normal initialization. And set the bias to be 0. F of L dot, let's see, F of L of 0 dot weight. I'm not sure what this function is doing here. Oh, F is the Keiming and normal initialization. Okay, fine.
I think you're just passing basically convolution weights is what you want to send. Is instance L nn dot sequential. So you're looking at only the sequential layers there.
Yes.
So that would be.
And F of 1 comma A equals. So what's A in the F?
That's the leaky, I think, right?
Okay.
So it's the leak that you're passing through.
Okay. Okay. Yeah. So that's the leak parameter. Okay. Let me just make a note here because it helps when you look through this again. All right. Now he redefines the getCNN model to include everything here. Is this being exported? Yeah, this is all being exported. So, okay. Now he defines this append stats function again to include the histogram. Okay, and here's where the histogram gets defined. It has 40 outputs between -7 and 7. I'm not sure what. So this is calling the hist_c function, which is actually the histogram function. And so this is a genuine histogram because I recognize the hist_c function from Python. I'm not sure about the histogram function that was defined up above here. I'm not sure that that's a genuine histogram. So I don't know. We'll have to look into that a little bit more. Anyway, let's run this thing and see what happens. Where are we here? To make sure we initialize, run. And now we're going to do this context manager method of running the training again. And here we have our plots. The first row is the first few samples. The second row is all the samples of the means. And this time we're only doing the first 5 layers. I guess we could ask for more if we wanted to see more. And then now let's look at the, now this should be the real histograms because I saw that he defined here, hist.append. No. Okay. So we are getting, in the append stats method, we are getting real histograms. That's, all right. So that's one thing I noticed here. So we're refactor append stats to add histograms. That's good. Now let's see what they look like. We've run it, and there's our histograms. I'm going to try to, I'm looking for a way, I haven't done this yet. I want to label these histograms because any plot is absolutely useless unless you have labeled the X and Y axis. There's just, you need to not only label them, but give me the numbers that are associated with them. So here, I believe these are the 40 values. He defined histogram with 40 bins, probably uniformly spaced between -7 and 7. And that's what these are, okay? That's what these 40, there's going to be 40 bins. That's what, so you're creating this 2-dimensional plot and making it look like an image. But what we're seeing is there's going to be 40 pixels this way and 108 pixels this way. So 0 should be the middle because we defined 40 bins equally spaced between -7 and 7. So this would be -7 and this would be 7, and 0 should be roughly the middle. So this, I'm not sure what these 4 plots are though. Oh, they're the 4 layers. They're the 4 layers. And we're plotting histograms. I'm not sure what the histograms are. Are we plotting histograms of means or histograms of standard deviations? I have to go back and see that. But anyway, let's just continue, push on, because I think we're getting close to the end. And then we have the
histograms of the activations.
Oh, the activations. Okay, histograms of the activations. Okay. Let me just, thank you for that. Add histograms of the activations. Okay. That's very helpful. So now we see them. And we still see that the majority, from these histograms, the majority of the activations are really concentrated near 0. So that's not good. And here's our getMin function. And, well, actually, maybe I'm wrong. From eyeballing it, that's what I thought. But apparently, he's demonstrating here that is not the case. Here, we see that now it's gone down to 40% of the activations are in the 0th layer. Well, between 30 and 40%, let's say 35%, the 0th layer, 35% in the first layer, but now it's gone down to like 20% in the second layer and less than 20% in the third layer. So this initialization is having a good effect. That's how we can tell compared to the last. Okay, now we export this new thing. He's refactoring get, learn, run, and I'm not sure what the difference is. And it looks like the same.
I think it's just that the difference in initialization, instead of using a normal, you use a uniform initialization.
Yes.
Or do you have to get on one of the two?
Well, uniform is a switch,
Right.
and uniform equals false means that you want to use normal initialization. But if uniform were true, then you would use uniform initialization. So yeah, this is just refactoring get, learn, run. And now
Joseph, just a clarifying question. For the neural network that you have, the active value, is it 0 or non-zero?
The activation, you want the activation to be away from 0.
So this is not a 0-centered activation function that's used in here?
Remember, the activation function is a ReLU, or is a ReLU, for example, a ReLU activation function is not 0-centered. Remember, the ReLU has a branch, the negative branch of the ReLU is 0,
right,
and the positive branch is an increasing, monotonically increasing.
Okay.
Yeah.
The uniform and normal over here is for the initialization of the layers.
Correct. Yeah. In other words, instead of when you do Keiming initialization, if it's uniform, you initialize by choosing from a uniform distribution centered at 0. But if you ask if uniform is false, that means you're going to choose a normal, that is a Gaussian initialization. And I think someone pointed out somewhere that Gaussian initialization tends to be concentrated towards 0, because you remember the Gaussian comes to a peak at 0. So most of the values of the Gaussian are going to be 0. You're initializing towards 0. But when you do uniform initialization, remember the uniform function is spread out equally from all the way from, -1 to 1 or -0.5 to 0.5, whatever. You're going to get a distribution that includes more non-zero values. And I think that's why they found that uniform initialization works best rather than normal initialization. Okay, so now he's going to build in a scheduler. So he defines the scheduler as we did in one of the previous notebooks. And now he adds, all you have to do, in other words, the get, learn function, get, learn, run function, you don't even have to modify it. All you have to do is change the list of callbacks to add the scheduler. And that's what he's done here. And now we're going to run 8 epochs with everything. He says that uniform initialization may provide more useful initial weights. And this is what I was saying before, because the normal distribution puts a lot of them at 0. But I think when I ran this, I found that normal initialization is just as good. So, and you'll see that here. Now we're going to force it. Okay, so before we were using default, which is uniform equals false, which means we were using normal initialization. And after 8 epochs, we got up to 98% accuracy. Now let's do it again, this time with uniform initialization. And when I saw this last time, I saw I didn't get any better. Yeah, it's just about the same. All right, so now we're at the end. We actually finally made it through Notebook 6. Just amazing to me how much Jeremy packs into these lectures. This one lesson 10 is going to take us 6 sessions to get through, because we're going to need another session to do Notebook 7. So thank you for hanging in there with me, everyone. And I'm done. Took us an hour and a half, or no, almost 2 hours.
A few questions, if you don't mind.
Sure.
Do you mind scrolling up to where we did those act means? Hang on, here we have, just can you scroll down one more?
Yes. Right here?
This is also 108, right?
Yes.
Okay. Can you scroll back up? Did you pull the recent version? Do you still have if self.training in your code when you're calculating?
I didn't. Okay, I haven't pulled from the repo since maybe a week or so ago. Has it changed?
Oh, then no, then I don't think so, because I was trying to add up that 108, and like you said, you get 98 for training, and if you use 10,000 for validation, and like you said, the data set batch size is 1024 there, right?
Yes.
So if you do 10,000 by 1024, you get 10, and the previous one, 50,000 by 512 gives you 98.
Yeah.
Kind of adds up there, right? 98 plus 10, 108.
Ah. So the last.
Yeah.
The last 10 of these is going to be the.
Looks like they're from the validation.
Ah.
But I don't know. This is what I think.
Yeah, that's a great insight. I think you might be right, because otherwise, where does this number come from?
But then I think if you look at the comments there, Jeremy did make a fix for, that's why I was just wondering if you have if self.training when you're calculating your telemetry or no.
Can you say that again? What are we looking for?
Self.training, if self.training.
Okay, I'm just going to write this self.train. I don't have any.
Okay, so that's the reason, I think, because from what I see, I can see only 98, and that's what he added in.
Oh, so when you do this, you only see 98?
I'm currently not able to run my notebook, so yeah, from what I see in my graphs, yes.
Okay, this is good. I'm going to pull from the repo.
Yeah,
and run.
if you could check that, yes.
Thank you, Prashant.
Yeah. Can you again make a quick search for sequential model?
Yes. Oh, that was already there. Okay, so this is this. We want sequential model?
Yep.
Sequential. I spelled it wrong. Sequential model.
There we go. Yeah. So in your call, I have if self.training. I'm just pasting this right now in the chat. So
okay.
That's where the difference.
So he modified this then, huh?
Yes.
So he's modified it since I've. All right. Great. I'm going to pull the repo and look at it again. But thank you so much for this insight.
Sure. Yep.
You've been terrifically helpful, Prashant.
Yeah, but this notebook is kind of hard to visualize and understand what those histograms are.
Yeah, this is one of the most complicated notebooks I've seen from him so far. So I'm glad we got through it. The next notebook is not as complicated. It's not as long.
Yep. I definitely want to emphasize your point that the histograms are terrible. It's actually very bad practice not to describe the x-axis and the y-axis, and we were all confused by it. And so I think this has to be reworked. I mean, you can't.
Yeah, I'm going to try to do that. I'm going to take that as an assignment for next week. I'm going to try to rework.
No, it wasn't meant to you, Joseph, obviously, but to.
No, you're right. I mean, it's like the way that it's done is just not. I mean, I really appreciate what they're doing at Fast.ai. They're working like crazy, and they only have like 2 people to do it, or very few people to do it, and so they can't pay attention to best practices all the time. But it's on us then, if we want to understand this better, to fix things up a little bit to help us to learn it better. So
I think the other main thing is that before you do chiming, there is something specific with the graph. That's what Jeremy talks about, the exponential drop-offs, which is supposed to be a sign of bad training. Whereas it kind of shows up in the last graph too, but to a much smaller extent. So yeah, trying to understand that so that next time when you run it on one of your networks, you should be able to pinpoint and say, oh, this is the problem. I'm trying to understand it that way, and kind of hard to figure out what is happening.
Somebody made the point, I think it was Yefim made the point that it might take you 40 40 iterations until you see, or 40 samples until you see all the, in each batch, it might take you 40 samples until you've seen all the numbers, all the digits.
But that might be. We figured out that the x-axis right now is basically number of batches, right? So it cannot take 40 batches for you to.
Batch number. Ah, so it is batch number.
Yeah,
okay.
It is batch numbers. So it cannot take 40 batches for you to see.
Yes, you're correct. Yes. So I have to go through and change all of this notation to batch number instead of sample number. Sorry about that. Yeah, so, but I think you've got it. I think that the 108 comes from adding in the validation batches, and that's probably a mistake. And so in the later version of it, he says, let's only look at the training, and then instead of 108, we should have 98, and that makes a lot more sense.
Yep. Yeah. Good
Thank
question.
you so much.
Cool. Yep.
Okay, everyone. Thank you so much for staying with me. I know it's been long, but I think we really learned something today. So.
Yep. Yeah. Thanks, Joseph.
Thanks, Joseph, very much. Yeah. Thanks for hosting.
Okay. Well, see you guys in about 3 weeks then, huh?